you measure coming off of that is going to end up being a function of formation of several different products. So experimentally, it's difficult to calculate the standard enthalpy information of ethane from its precursors. But this is where the fact that enthalpy is a state function ends up becoming very useful. So we said that for state functions, they're independent of path. So the change in enthalpy, can be calculated along many different paths. This is just one particular path that theoretically you can calculate the enthalpy on. It's experimentally a very difficult path, but if we had a handful of different reactions that summed to this total reaction, and we knew the enthalpy changes for all of those reactions, then we could kind of paste them together in a way that, or link them together in a path that led from carbon and hydrogen to ethane, and sum the enthalpy changes in those paths, and it would equal the same thing, right? Now it turns out that very useful chemical reaction for doing these is combustion reactions. Combustion reactions are where we combine things with oxygen and let oxygen come in and do its thing, right? Oxygen is very electronegative. It comes in and just pulls electrons off of everything and drives reactions. It drives them very quickly. It drives them almost entirely to completion. And so it's very easy to calculate the enthalpy change for a combustion reaction, whereas the enthalpy change for this is very difficult. So let's look at how we can paste together a series of combustion reactions that end up summing to this reaction overall. We can combust ethane. We can take C2H6 in its gas phase, put it in with 7/2 moles of O2, gas phase, run the combustion. Products are going to be CO2 in the gas phase, 3 H2Os in the liquid phase, and if we'll witness some delta H. I didn't write down what that was, so I stole this example from the text. The text didn't write it down, so I didn't bother to look it up. But you throw some ethane and some oxygen together, run the reaction, they're going to combine. It's going to go almost to completion, or almost entirely to completion, forming carbon dioxide and water, and you'll witness some heat transfer, some enthalpy change for that reaction. You can take graphite and add to it oxygen in the gas phase, so carbon in the solid state, oxygen in the gas phase. Run a combustion reaction on that, and you're going to form carbon dioxide. And you'll have some other enthalpy change that you witness. We'll call that delta H2. Right? Hydrogen. Take that guy in the gas phase, combine it with 1/2 mole of oxygen, run the combustion reaction, form water, and we'll get some other enthalpy that we can measure. These reactions all happen very readily, and they involve heat. It's very easy to capture the heat, quantify the heat that comes off of that. These three equations can be rearranged such that the sum is equal to that equation that we were looking at up there for the formation of ethane from graphite and hydrogen. And it looks something like this. Take this reaction with carbon and oxygen, multiply by a factor of 2. Draw a little line here to show them going through a different process. And the enthalpy change is going to be 2 times delta H of 2, right? We take that reaction, this guy right here, we flip it around, so we've got 2 CO2s plus 3 H2Os. Going to form ethane. And the enthalpy change is going to be the negative of this guy, so we'll call that negative delta H of 1. And then we take that last reaction, that H2 reaction, we multiply it by 3. That would be 3 times delta H reaction 3. End up summing these together. The O2s cancel with each other. CO2s cancel with each other. The H2Os end up canceling with each other. And the sum of the reaction, the sum of those 3 reactions, ends up being our reaction for the formation of ethane from its elemental precursors, right? And so the total enthalpy change is going to be the sum of those 3 enthalpies that we measured using combustion reactions. So these tables that were generated, a lot of the reactions they didn't actually take the elemental precursors and react them and measure the enthalpy changes. What they did is they took advantage of the fact that enthalpy is a state function, and they took reactions that were easy to measure, reactions that went to completion, and then reconstructed reactions from elemental precursors to figure out what the enthalpy changes were. Right?
What do you mean when you say state function?
What's that?
What do you mean when you say it's a state function?
A state function is a function that is going to be the same. It's going to have the same value when you move from one state to another, no matter what path you take between the 2 states. So early on, we said that internal energy was a state function, right? And internal energy is the total energy content of a system when it's in a particular state, and that kind of makes sense to us, you know. Or if we're in one particular energetic state, we always have the energy associated with that state. It doesn't matter how we got to that state. It's just something that we have. It's our internal energy. So internal energy was a state function. Mathematically, state functions have an exact differential. They're independent of path. And then we showed on Tuesday that enthalpy was also a state function. And that's kind of what provides us with the ability to calculate changes as we move from one state to another in a variety of different ways. It's that independence of path that allows us to mathematically reconstruct this reaction by summing several different steps that ultimately lead to the same reaction sequence, right? The same total reaction. Not sequence, but total reaction. All right, so real quick piece of work for you guys. I'm going to ask you to do something. Oh, so what we're talking about here is Hess's law. In your book, this whole thing we just discussed is referred to as Hess's law. I want you to calculate the average bond enthalpy of OH in H2O liquid. So the reaction that we're looking at is H2O in the gas phase becoming two hydrogens in the gas phase and one oxygen in the gas phase. And the bond enthalpy is the enthalpy associated with breaking a bond. You know, the bonds are low energy states, so if we want to break them, we're going to have to put some amount of energy into them to break them. And what I'm going to tell you is that I've got a series of different reactions that I know the enthalpies of. I know that if I take 1/2 H2 in the gas phase and I break it apart into hydrogen gas, that I will get a delta H of 218 kilojoules per mole. If I take 1/2 O2 in the gas phase and I turn it into oxygen in the gas phase, delta H is going to be 249 kilojoules per mole. And if I take 1/2 O2 in the gas phase, I add to it H2 in the gas phase to form water. Gas phase. Actually, is that liquid? It might be gas. That we got negative 241.8 kilojoules per mole. Yeah, so we're talking about gas phase there. So your job is going to be to take these three equations and to sum them together to form this equation. Tell me what the enthalpy change is associated with that. And then you're going to need to know that the total enthalpy change associated with this process can be thought of as the enthalpy associated with taking a hydrogen and breaking it off of an oxygen 2 times. Right? Because we've got 2 hydrogens bound to oxygen. When we turn that into 2 moles of hydrogen gas and 1 mole of oxygen gas, we've effectively broken those bonds in the oxygen. So sit on that for a second, see if you can figure out what the enthalpy change is.
On that, like, every product is like reactant products, right?
What's that?
Reactant products, reactant products.
Yeah, yeah. But you can flip those around, and all you have to do, if you have to flip them around, you just change the site on the enthalpy.